So we're starting week 3 here. Tomorrow's lab is Charles' Law, and that's going to involve like boiling water and air. So safety goggles will be optional for this. Exercise A, safety goggles is going to be optional. You can wear safety goggles for splashes, maybe some impact protection, splashes of water, hot water. You'll want to wear shoes, though, like open sandals. You need some foot protection. The foot protection is for broken glassware and spills in lab. So if you have open-toed sandals, you might get cuts and stuff from glass that might not have been completely cleaned out. But next week on Wednesday, which is lab day, we're going to have our first exam 1. And so the material that's going to cover, through chapter 3, probably 4, which will be gases, and 5 will wait until later. But also you'll have a little bit of nomenclature, like these 10 ones that you can't figure out based on the pattern, that you have to just outright memorize. Memorize those for the next test.
Well, you're given the periodic table for the exam, but it's not the chart, it's just the random parts, right?
These ones here, the monatomics, yeah. The exam will focus on the polyatomics, but the charges you can get off the periodic table. You'll have the periodic table. It just won't have the name of the element on there. And so you'll need to know the names. But the charges we know, like these are going to be 0 charge. These are what? -1, -2, -3. Yeah, this is like kind of midway. These ones, it's closer to add electrons than take away. When we get the carbon, we could either add 4 electrons or remove 4 electrons. It's midway between the range. The range is, what's the range on carbon?
+4 to -4.
Yeah, +4 to -4. That's right in the center. This one's going to, however, likely not negative, +3. So we're going to switch. Now, getting a -4 or a +4 means adding a lot of electrons. That's actually 4 electrons, or losing 4 electrons. It's hard to do. And so what we tend to see is that these don't form what we call monatomic ions. Monatomic ions would just be alone and with a charge. That the negative or +4 is in conjunction with other elements to help stabilize that charge. Because it's high charge. The higher the charge, the stronger the more unstable, the stronger, what was that called? The stronger talking in the jargon of chemistry, the stronger what was that law that deals with charge and electric? The stronger the force, but what kind of force was that?
Was it electromagnetic force?
Yeah. It would be electrical forces in this particular instance. Yeah. And what was the law? Dan? Nicole H. So it's not that I'm going to necessarily ask you what the law is, because you don't necessarily have to memorize it, but the thing is how best, there's certain things that you have to memorize in chemistry. It's not like a history class. I'm going to ask you dates. What date was Lavoisier doing his phosphorus combustion experiment. That's not that important, but this is one of the laws of nature. One of the laws of nature, which we talked about, and actually it's the most important law for chemists. quantum mechanics, but quantum mechanics is kind of based on this. Quantum mechanics is a more sophisticated version of this, a much more sophisticated version of this. This is a very simple law I wrote down on the slide. But the best thing you can do, and it is this: if you're like me, you don't have great memory, and if you don't have great memory, you need to do this every day and in repetition. You see it every day. Then it's a lot easier to memorize. This is why advertising helps. You know, advertising, they want you to see it every day. If you see it every day, you'll remember it. Otherwise, you'll forget it, right? And if you don't see it every day and you just see it the night before the exam, it's really hard to remember. Well, that's based on personal experience. Maybe you're different, I don't know, but if I'm asking you and nobody can recall it, then you definitely need to do something. Whether you take this advice or you do some other advice, you need to know certain basic knowledge. And the problem is that people try to cram it the night before the test and fail miserably on the test. And so do whatever you do. I mean, the test is next week. You got to. No, what was the law? This is kind of an important law in nature. The thing is, do you have it in your notes? That's number one. Is it in your notes or not in your notes? Or maybe not. Or maybe I didn't talk about it. No, not that one. Has to do with the pith balls. Do you remember the pith balls? These ones? You ever talk about this? Uh-huh.
Was it Coulomb's law?
Coulomb's law. Good. So one person has it. Coulomb's law, you don't really need to know. What I do is when I do this, I try to put it in words I understand. And so can you rephrase Coulomb's law into words that you may understand, or just kind of summarize it in a way that you can remember it? You know, I don't know why I didn't save the annotations here. So what I try to do is, okay, I have this is the essential form for Coulomb's law here, ZA, ZB divided by D squared. And so what I'll say is just, it depends on the magnitude of the charges on A and B. The bigger the charge, the stronger the force. It also depends on the distance between the center charges squared, and it's squared, so the effective distance, it drops off rapidly. So the further apart they get, the much weaker the force becomes. And so this is related to something called charge density. Charge density is how concentrated is the charge. If the charge is very concentrated, then it's going to have stronger forces. If the charge is diffuse over a large volume or a large area, it's going to have much weaker. And so it depends on how you concentrate that charge. And so this is the way I think about the distance. So, but that's Coulomb's law. You don't have to know the mathematical form of Coulomb's law. You just have to know that the bigger the charge is, the stronger the force. The shorter the distance, the smaller the volume, the stronger the force. That's it. This is the fundamental force in chemistry. You know, I talked about why the water molecules are sticky. The reason they're sticky is because of this electrostatic force of attraction. And cisplatinum's an anti-tumor drug, you know, and the way that works is it gets stuck in the groove of the DNA. How does it get stuck in the groove of the DNA? One, its shape is right, but not only is its shape right, but the electrostatic forces are there that makes it stick in there and prevents that from happening. It's the same thing for carbon monoxide poisoning. With carbon monoxide poisoning, we have those forces with carbon monoxide and hemoglobin. And so this is important in chemistry, and this is why they talk about the electrical character of matter. They devote 2 slides to this slide and this slide, but this is really chemistry here. The water molecules stick together because they're like these pitfalls, and they kind of get stuck, and this is what holds the liquid together. There's this fountain in downtown Los Angeles that shoots these gigantic water droplets. And you can watch them. These water droplets shoot up, and the water's like a giant blob, and it looks like the molecules are trying to break apart, and things are trying to vaporize, but everything's being held together. So you just see this like this cannonball, but it's a really soft liquid cannonball rise, and it doesn't stay a sphere, you know, because it's trying to break apart, but it can't break apart. Have you seen that fountain? It's where is it by? It's like Hill Street and one of those. It's pretty fascinating watching the droplets there, you know. And you think about the water molecules are kind of just stuck together by electrostatic or coulombic. Electrostatic coulombic forces we call the same thing.
Coulombic?
Yeah, Coulomb. This is Coulomb's law. Where did Coulomb's law come from? Where do laws come from? There are 2 ways laws come from, or two methods people derive laws. This is Coulomb's law.
Numerically and theoretically?
Yeah, where do you think Coulomb's law came from? Empirically, yeah. This came from the empirical data. You look at the force of attraction and you measure it. Kind of thing. It's empirical. Later on, of course, it can come from theoretical as well. But laws are important. But you don't have to know the theory to apply a law. You know, laws we can use. They turn out to be very useful because those are consistent, reliable patterns. If you have consistent, reliable patterns, then we can predict that those are reproducible patterns. Versus inconsistent, random patterns aren't going to lead to such things. There's I've been watching a couple of these videos here. Let me show you. You might be interested in this. Do you know who this guy is? This guy is a professor at Harvard. He's like the head of the astrophysics or astronomy department or something like that. But do you know lately? This is Avi Loeb. There's a interstellar object that was observed in Hawaii, and it had some very unusual properties. And so this intrigued his attention. And so based on the properties of this, one, it's moving very fast. It's coming outside the solar system, and that's rare. And 2, the way the light reflected off this was very unusual. It wasn't like normal rocks. And so based on these observations, he came up with a hypothesis. You know what his hypothesis was? His hypothesis was that this interstellar object was not a rock. It was an alien. It was constructed from some kind of alien thing. But you might think, oh, gosh, another alien. But
59 years old, and I'm having more fun than I did in my 30s.
I feel really good,
of
especially
course, there
since
are
I'm
other
not in the
hypotheses.
gym doing any kind of workouts with the weights.
Which hypotheses do you
definition
believe?
of my
Because there are
legs,
people who are
my
totally
bicep.
skeptical. I mean, this guy
even though he's
do
a
something
professor at
different than
Harvard,
a
this
rock.
guy's ridiculous
And
because he's
it's
claiming
just
aliens
like the
exist,
kid in
right?
Hans Christian
And,
Andersen's tale.
And it's pretty
who
interesting
looked at the
because
emperor and said the emperor
he talks
is
about
naked. The emperor
what
has
kind
no
of proof
clothes.
does he
And
have
all
for
the
this
adults in the room said,
existence
"What do
of
you
aliens?
mean?
It's just strictly
It
based on
the
these
emperor has clothes. You just
observations,
can't
these
see them.
unusual
And
observations.
in this case, the clothes are
And
the
of course, they're
evaporating gases
competing.
from Oumuamua.
Competing. What do we call them? Competing theories
Wow.
or competing hypotheses?
That story is
Competing hypotheses.
quite intriguing. And
So
also
it's
piques
interesting.
curiosity.
He's
And
talking
like
about
you
the
say,
competing
Professor,
hypotheses here. So I thought
And then,
I'd play
the
this
problem with
part
that-
here.
Is it maybe like pattern he's going based off?
Yeah, based off patterns. These patterns are not observed. These are very unusual. Actually, this pattern's never been observed before in nature, and so this is why this intrigued him. And so you think, what kind of evidence? Well, this guy's interesting because there are other things that people see, like the planes come across these unidentified aerial objects. They call them. They don't call them UFOs anymore, but UAPs or something like that. Well, anyway, so he doesn't want to see these at random. So have you heard of this Galileo project? Galileo project is constantly monitoring the sky, looking for these unidentified aerial phenomena, UAPs, because they don't want to see them at random. He wants to see them and then measure them precisely and accurately. And so that's what the Galileo project is there, I think. But this is interesting here. Let's see if we got any audio for this. If we don't, then I might play it. But of course there are going to be competing hypotheses because scientists in general are skeptics. They aren't going to believe this. This crazy aliens or whatever.
Hundreds of degrees. Then there was a suggestion, maybe it's a hydrogen iceberg, something we've never seen, made of hydrogen, and then when the fact that it was not...
I don't know what's wrong with the audio with this thing, so I'll play this in lab. Not only that, there was a meteor that came in, and this is not meteors have been studied, a lot of them. And actually, I took a meteor class. There's a professor in the geology department at UCLA that decided to take his class. It was a graduate class when I was an undergraduate there. He was a geochemist, and he studied meteors. He wrote a book on meteors. So most of the meteors, they had the chondritic meteors, and they have the iron meteors. So those are pretty well studied. But this meteor is very different. For one, the speed of it. And then two, the other unusual observation was it didn't break up like a normal meteor does. It lasted a much longer time. So he's thinking, how could this last much longer before breaking up? And so he's thinking, well, it must be from, he hypothesizes maybe it's from alien technology. And it's made up differently than the normal meteors are. And so he took an expedition to the ocean and then scraped the bottom of the ocean for parts of the meteor and then had those analyzed. And it's pretty interesting because the elemental composition of that is a very unusual alloy containing uranium and a few other elements that you've never seen before in combination. So this is why he's thinking that could have been an alien probe that broke up, or alien junk that came in. And so it's very, very interesting. But this is how science is supposed to work. A lot of people will say this guy's a nut job, but he has his arguments. Other people, and then the other people proposed that's a hydrogen iceberg. But he said, no, it can't be a hydrogen iceberg because it wouldn't have lasted that long and at the speed it was moving. Vaporized. Then another hypothesis was it's a nitrogen iceberg, but he has arguments against that as well. And so it's very interesting. This guy's written over 1,000 publications, and so this guy really was quite sharp. And so you listen to his arguments, and then of course, Harvard hasn't kicked him out of the yet, but who knows. But this is the same thing that happened to Dalton, of course. there are going to be lots of skeptics for Dalton's atomic theory, but when you look at the competing hypotheses, what's the supporting evidence for the competing hypotheses, and how does it fit for the one that you see here? You know, how can you get just the right amount of hydrogen and oxygen? When you try to mix sugar and flour, do you always get the perfect exact same ratio of sugar and flour each time you mix it? Well, that would be like infinitely divisible matter, because if matter were truly infinitely divisible, then it's just like taking a whole bunch of powdered sugar and powdered flour and then trying to get the exact same mixture each time. But how we know that nature works is it's more random. You have these random collisions, and when you form things, like when you form cisplatinum and transplatinum, you try to make one, but it often happens you end up making both. It's like Advil. You know, half the Advil, like ibuprofen, is wasted, you know, because half of it is like wood. You know, can we eat wood? So it's like, it's like in nature, let's say half of it you make wood, the other half you make sugar, like starch. You can eat the starch, but the problem is it just happens at random. And so you end up with what we call a racemic mixture. You end up with 50-50. And so that means tons and tons of ibuprofen's wasted because we can't digest it. It's like trying to digest wood. And the other half that's made, we can digest. You know? And so that's a big topic in chemistry. A big topic in chemistry is trying to structurally design the synthesis so it doesn't happen at random. You know, it's more predicted to form one form over the other, or at least more, in other words, designed to synthesize exclusively one form, and then we don't have tons of waste. It's very expensive, that waste. You know?
Question about the periodic table.
I'm sorry?
Question about the periodic table. Is there 118 elements? It's like 1999, right?
Well, this is, you know, there are other people who claim alien life form. There's this guy, Bob. I don't know, I just started, clicked on one, and then I got a bunch of aliens ones. But this guy that used to work at Area 51 and S2, have you ever heard Bob Lazar? He's been interviewed a bunch, and he's back from the 1980s. Well, he claims there's an element number 115, and the element number 115 is what's responsible for distorting gravity so that things can travel interstellarly. Have you heard that? But, you know, element 115's been synthesized, and then he says, okay, if you take element 115 and bombard it with protons, then you're going to distort gravity, and then you can have these UAPs that can kind of defy the laws of physics because they change gravity, basically. And then, obviously, if you change gravity, Newton's laws are based on gravity, you all know that. So if you change that, then you can have that. Well, that's a case where a lot of skeptics, and he hasn't come up with good arguments as to what. Because element 115 has very short half-life. The elements up to about 120 have been synthesized. So this is an old periodic table, and then there's current debate, you know, because when somebody claims to have synthesized it, other people want to repeat it to see if they did the same thing. So element 115 has been synthesized and has been studied, and the most, at least what we call the most common form, this is isotope, has been studied, the properties of that. And so based on the observations of that, then Bob Lazar is on shaky ground. You know, it's easier to, unless he has some stronger arguments as to how it works, he's going to have more skeptics than believers. However, that's fine. Bob Lazar, he can hypothesize that. That's fine. What we need to do is we need to have supporting observations or supporting evidence for either his pro Bob Lazar or counter Bob Lazar. And so this is the way science is supposed to work. But you know, you aren't supposed to say, okay, he's a nutcase, and don't listen to him. Well, we can listen to him, but you want to hear his arguments and the supporting evidence that he has for such stuff. And then that's the way you can either disregard what he's saying or pay attention to it. But to outright censor him, no, that would be not the way science is done. Although there are lots of people who want to.
censor him. Just like there are lots of people who want to get rid of him, this person. But, you know, it's good to have competing hypotheses, and then that's how knowledge grows. In fact, he has a great quote in here about knowledge, how knowledge grows from observations and experiments. But, you know, the speed of this, you know, what the hypothesis, how is this thing moving, you know, and the technology thing is very thin. All right. So we're going to go through this quickly. There's a lot of slides in this, so I'm going to skip the learning objectives here. And scientific notation, you know, you could review this. There's a math review in our book. I'm not going to go through this because this is part of prereq for this class. So you should be able to switch from decimal to scientific and scientific to decimal back and forth. So just converting scientific notation here in decimal, some examples of that. And then the exponent here, you know, negative versus positive, negative for small numbers here. And the reason we use scientific notation is because we work with extremely small and extremely large things.
Also for precision, right, and accuracy.
I'm sorry?
Also for precision and accuracy.
Yeah, also we pay attention. We pay attention to precision, accuracy, and there are a couple of more things we pay attention to in measurement, which I haven't really talked much about. One is systematic error. I did talk about it a little bit. Systematic error, and what was the other error? Systematic error we get rid of by calibration. You know, make sure we're calibrating things, or make sure our eyes are level with the meniscus, you know, not parallaxed. And the other type of error we take care of by the other type of error is what we call random error. We'll talk about that later. And so whenever we do measurements, we think about precision, accuracy, systematic error, random error.
How do we solve random error? How do we solve random error?
We solve random error by taking multiple trials. So let's say trial 1, you know, 15 milliliters, I got this density. Trial 2, you know, we want to confirm it and see. Trial 3. So based on statistics, if you take an infinite number of trials, then the high ones should cancel out the low ones, and we should have the true average. But it's impossible to take an infinite number of measurements because, you know, sometimes you're over here, sometimes you're over here, but, you know, eventually you'll converge on the real answer. And so the best compromise is in science, you know, usually when people have more involved experiments, they try to get at least how many trials to average? 3. And there's statistical validity to that because taking one trial, you're highly at risk of some random error. If you take 2 trials, you start to minimize that risk. But if you take 3 trials, the amount of risk, it's non-linear, so it's not 3 times better, it's much more, you know, than 3 times better. And so it's like 10 times better, something like that. But if you take 4 trials, the benefit is much smaller, you know. And so the difference between, let's say you took 1 million trials and 1,000,001 trials, is there going to be a huge benefit in taking 1 extra trial? No. And so that payoff diminishes. There's a law of diminishing returns in a way. And so most people compromise at 3 because that gives you the best return for the time invested. So
Do you go by mean or by the most, the lower the median when it comes to
the mean. We'd use the mean. We don't use the mean. We would use the median if you have a lot of trials. Then we might use the median, but we always use the mean for everything, pretty much. All right, different calculators will have different keys for scientific notation. So when you do scientific notation, when you hit the EE or EXP key, that's automatically putting times 10 and then you just put the exponent in there. So what sometimes people do is they add another 10. So if you notice that you're always off by an order of magnitude, let's say the correct answer is 10 to the third, but you're getting 10 to the fourth or 10 to the second, then it could be the way your calculator keys it. You're adding an extra 10 you don't need to. So sometimes that happens. And so we'll talk more about this. This is just converting. If we have 50 minutes, how many seconds is that? And so this is what we call a common conversion here. There's 60 seconds in a minute, and if we multiply these two, then the minutes cancel out and we're left with seconds, so there's 300 seconds in 50 minutes. This is the standard problem-solving approach that we use. This is called dimensional analysis. Dimensions are the units here, or factor label analysis. I think your book calls it factor label. And all it is just making sure the units cancel to give you the correct units. And this thing is called a conversion factor. This is the relationship between minutes and seconds. I would ignore this blue one here, as not everything's set up like that. And so,
Factor label, you say?
factor label or dimensional analysis. I call it dimensional analysis. But this is not really. What they're saying is that this would be the quantity, 3,000 seconds. In a quantity, we have the value, which is 3,000, and the units, which is seconds. But you don't need to know. I'm not going to ask you what the value is, what the unit is. It's just, when you take a measurement, there's going to be a unit associated with it. And so this one, don't bother. This. So the oldest horse racing track in the United States is the 8 furlong Pleasantation Fairgrounds racetrack in California. What is the length of the track in rods? Furlong and rods, I have no idea. But we're given 8 furlongs here, and we need this. And they tell us they're 0.025 furlongs is equal to 1 rod. So 1 rod per 0.025 furlongs. And we've got to make sure it cancels out. And so this is a relationship between rods and furlongs. And if the furlongs cancel out, that'll just leave us with rods. So this is what we call dimensional analysis. Dimensional analysis, we just look at the units again here. This one, the furlongs and rods, I'm not going to ask you about furlongs and rods, so you don't worry too much about that. When we have an equivalency, like furlongs and rods, then we can express that in terms of a conversion factor. And so if we know that there are 0.025 furlongs per rod, that would be the equivalency. So it says 2 conversion factors result from each equivalency. So 0.025 furlongs is equal to 1 rod. That's the equivalency. Now, the 2 conversion factors that we get from this, the first conversion factor could have 0.025 furlongs on the top and the rods on the bottom. And what we use this one to do is we use this one to convert from rods into furlongs. So that we hopefully we get the rods to cancel out. So if I had 100 rods, how many furlongs would that be? Well, 100 rods times this, the rods would cancel out, and then I multiply that there, and I get 2.5 furlongs. The other conversion factor that we get from this is just invert this. So we'll put the rods on the top. So we have 1 rod on the top, and then we'll put the furlongs on the bottom. So if I had 100 furlongs, just multiply this by 100. So that would be like 4,000 or something. And so make sure the furlongs cancel. It's supposed to say furlong there. And so we just get two ratios like that, and then we use those in an algebraic calculation that was shown earlier. And so what we want to do is we want to just use conversion factors. Sometimes we have to stack one on top of the other. In other words, we do these in steps. Sometimes we just do it in one step. And so here are some examples. I'm just going to go through this kind of quickly. Because, 1 day is 24 hours. So the two conversion factors, 1 day per 24 hours or 24 hours per 1 day. My car averages 17 miles per gallon. So 17 miles is equivalent to 1 gallon gasoline. 17 miles per gallon or 1 gallon per 17 miles. So those would be the conversion factors that we use. All right, so this is this. And so basically I have an algorithm here. This algorithm I just put in my own words. In my own words is we start off with a given quantity and then we just add conversion factors until we get the desired thing. And so that's my thing here. So here's where we have to string together more than one conversion factor. Calculate the number of weeks in 672 hours. Okay, one, do you know how many hours per week?
168.
Is it 168? Okay. Well, if you don't, then you know some others that we can string together. And so our given is 672 hours. So this is what I do. I just start off with 672 hours, and then I need something that relates hours to something else. So I want something with hours in the denominator so I can cancel out the hours. So one thing I know is that in 1 day there's 24 hours. So I can go from hours to days. Here, cancel that. Then I add another conversion factor here. I need to cancel out days. And so I can go from days to weeks. And so here, it turns out it's 4 weeks. That's basically the technique that we use. We just try to cancel it out. I do it one step at a time. I don't necessarily have the whole route, that is, path, or whatever, figured out. And so I just do it one step, and then I see where I'm at. Sometimes I do it like, for example, here, I could have gone 72 hours, cancel out hours, and I could have just said there are 60 minutes per hour. And so if I did 60 minutes per hour here, so I change this 60 minutes on the top, 1 hour on the bottom, would that get me closer to where I'm going or further from where I'm going? So where am I trying to go? I'm trying to go to the number of weeks. And so if I'm going from hours to minutes, is that better or further? That seems I'm getting further, I'm getting colder. And so I don't want to do that. Even though I could have gone from hours to minutes, no problem, because I know the conversion, I know the relationship in the 60 minutes per hour. But if I go from hours to days, that's getting me closer to weeks. And so here there are potential forks you can go, but we try to get to where we're going, weeks. But I don't know the exact path I'm going to use to get there, but I just want to get there closer with each step. What distance expressed in miles will an automobile travel in 3 hours at an average speed of 62 miles an hour? So we have we're given two things. 3 hours is a fixed amount of time, but 62 miles per hour is what we call a intensive property. So 3 hours is what we call extensive property. So let me give you some other examples of extensive versus intensive. 3 hours, time's an extensive property. It depends on the amount. Mass is an extensive property. It depends on the amount. So like 500 kilograms. It depends. However, density does not depend on the amount. So let's say I know the density of water. It's about 8 pounds per gallon. Does that depend on the amount? Let's say I had 1,000 gallons of water versus 1 gallon of water. Does the density change? for water? No, it's still that same ratio. It's 8 pounds per gallon. That's what we call intensive or extensive.
Intensive.
Intensive means independent of the amount. Extensive means it depends. Now, what about the volume of water? Is that extensive or intensive? The volume of if I had 1 gallon versus 1,000 gallons, that is extensive. So normally when we look at a problem like this, okay, this is extensive or intensive, 3 hours.
Extensive.
Extensive. And then 62 miles an hour, that is intensive. So normally when we start a dimensional analysis problem, we start with an extensive quantity. You know? And we usually use these intensive ones as conversion factors. And so, for example, if I didn't go 1 hour, let's say I went 1.5 hours, how far would I have gone? You know, that ratio doesn't change. That ratio is still the same. It's you're driving at 62. If you're driving at 62 miles an hour, does it matter if you drive 1 hour, 30 minutes, 2 hours?
We got the same amount.
No, it's going to always be the same ratio. For every hour, you'll go 62. So if you went a half hour, you'll go half of it, 31. Right? That ratio always stays the same. That's intensive. So when we do these dimensional analysis, we might be bombarded with a whole bunch of quantities here. Which quantity do you start with? Which quantity you want to start with is usually the extensive, unless they're asking you for new ratios. So that is, unless they're asking you, okay, 62 miles per hour, what is that in kilometers per hour? Then we'd start off with the intensive because they just want a new ratio, kilometers per hour from miles per hour. But in most problems, not all, but in most problems, we're going to start off with the extensive amount. And so that's part of the algorithm there. This is my algorithm. I start off with extensive. So I want to start off with 3 hours. Now my algorithm is very simple. My algorithm is just do one step at a time. One step at a time is I have hours. So I need to cancel out hours on the bottom. So I can go from hours to minutes. Should I go from hours to minutes? So I go hour to minutes? No. Should I go hours to days? No. And the reason is because they give us a new one. And I can go from hours to miles. So now I have another one this one's only valid for this problem. Hours to minutes is valid for any problem. Hours to days is valid for any problem. But hours to miles, okay, we can use that. And that's more specific. That's going to get us to where we want to be in one step. You see that? And so this is my algorithm is, okay, I got hours here. What are all the things I can relate hours to? And that's what I'm going to do. Now, if I want to go kilometers, I might, I'll need something that gets rid of miles, and converts it to something else. If I want to go, let's actually do that here. I want to go kilometers. And so if I wanted to go kilometers here, I was driving my sister's car. She lives in Wyoming, but I don't understand why her car, she has the speedo set to kilometers per hour. And so this is just recently. But anyway, let's try to figure it out. How many kilometers were driven? And so what I need to do, this is my dimensional analysis algorithm. I need to get rid of miles. But where can I go from miles? I can go from miles to...
2 kilometers?
Do you know it? Do you have it memorized?
I know it's less than 1. No, more than 1.
All right, then let's try not to use that. Do you have anything with miles memorized? You might not. Do you know what the definition of miles is? 1 mile is defined as... You might not know this one. 5,280 feet is exactly 1 mile. So let's try that. Am I at where I want to be? No, I'm not at kilometers, but at least I'm one step. This could be a dead end, but I don't care if it's a dead end or I'm getting there. It doesn't matter. What we want to do in problem solving is we want to make an effort to get somewhere. So a lot of people will draw blank and then they leave the page blank. If you leave the page blank, then there's no way you're going to get any credit. So you might get partial credit if we go dead end or something, or we get stuck. But at least we did one step. And so, you know, when you climb a mountain, like if you're going to climb Mount Everest, you don't want to think, oh, that's way too many steps. You know, it's going to be too overwhelming. I was watching another YouTube about these people. They do 10 feet in 1 hour, and so they just do one step at a time. They'll just do one step rest, one step rest. You know, one step. And so this is the same thing we do here. We do one step, we rest, and we see, are we getting any closer? You know, are we going sideways? Are we going backwards? Or are we going up? You know, and so we want to determine that. And so I don't know if this is going to lead to where I want to go, but at least I'm making progress. And so the next thing is we need to get rid of feet. And so I need to get rid of feet. What are all the relationships with feet I can think of? I could go feet to yards, or I could go feet to inches. I don't know feet to meters. I don't have that. Does anybody have feet to meters memorized? No. But we do have feet to yards and feet to inches memorized. And let me tell you, I'm going to go to inches because it might seem counterintuitive because we're going smaller and we want to go bigger. Kilometers is much bigger than an inch. But I'm going to go to feet to inches because there's one other one. And so this is what we call a definition. In a definition, we use this. It's 5,280 feet, and then we use 3 lines is equivalent to 1 mile. And when we use that, the definition shown by these 3 lines here, this is what we call exact. So it's not approximately 5,280 feet, it's exactly 5,280 feet because that's how it was defined. Versus this. You might say, you might know this, but they're approximately 1.6 kilometers in a mile. Right? Just a kilometer is shorter than a mile, or approximately 2 kilometers in a mile, but that's getting less and less precise. But this is exact. And how about this? Is it approximately 12 inches in a foot, or is it exactly 12 inches in a foot? It's exactly. So this is also another definition. And so the nice thing about definitions is definitions are always exact. So we can show this with 3 lines. 12 inches, 3 lines, 1 foot. That's by definition. Now there's another definition that you may not know. And that is the definition between inches and centimeters is defined. And it's exact. Do you know how many centimeters are in an inch? No. An inch is, an inch is about this long. A centimeter is shorter or longer? Shorter, but how much shorter?
10?
No, 10 centimeters is like this. 2.54. They're exactly 2.54 centimeters in an inch. There's no uncertainty. It's not approximate, it's exact. And so some people might say they're approximately 3 centimeters in an inch. That would be very imprecise, right? But they're exactly 2.54. No fewer, no more than that. And so if we could do this by all definitions, or as many definitions as possible, that eliminates uncertainty. is uncertainty is sometimes people say how many liters are in a gallon. Some people say 4 liters in a gallon, but that's very approximate. There's a lot of uncertainty in that. It's not. We'd like to know exactly how much. And so this is why we like to use exact. This 62 miles per hour, is that exact or approximate? It could be exact, but if the person were actually driving, you'd say approximately. And so they could be anywhere around there. If this were a hypothetical thought experiment, then you could say hypothetically if they were traveling exactly 62 miles an hour, what's the distance in 3 hours? Exactly 3 hours. So these types of things we think about in terms of certainty and uncertainty. Uncertainty and certainty are very important in science. In science, we want to know, the thing is, everything has uncertainty. Unless it's by definition. So what that means is every single measurement you take has uncertainty. Now what we want to do is we want to understand the degree or the level of uncertainty in that particular measurement. And so in addition to, what have we talked about? In addition to, what were we talking about earlier? Accuracy, precision, random error, systematic error. We need to talk about uncertainty. How much uncertainty do we have? Of course, the professor, Avi Loeb, of course he keeps an open mind. He's not fixed. If somebody else has a more convincing hypothesis that the evidence supports, of course I'm sure he's open to that. Because there's a lot of uncertainty. How do you prove that that's alien technology? Well, how you prove it is that aliens jump out of that thing, and then that's proof. But that would be no uncertainty there, But there's always going to be that uncertainty, and we always live with that uncertainty, and we try to minimize that uncertainty. That's what we do, and this is why we try to use exact. These are called exact conversion factors. And the exact ones we try to memorize. The approximate ones we don't. Okay, so this one here is a new one. Actually, maybe these two. This one everybody already has memorized. This one you may or may not have memorized. 5280. And so this one, maybe it's useful to memorize, maybe it's not useful. But it turns out this one is extremely useful. This one you need to memorize. And so memorize this next. If you don't have this one memorized, of course memorize this one. 12 inches in a foot. All right, what's the next one? The next one we don't necessarily have to memorize, but we need to get rid of centimeters. Okay, do you know any relationships between centimeters and anything else? 1 meter. How many meters in a centimeter, or how many centimeters in a meter? 100 centimeters in 1 meter. Is that exact or approximate? That's by definition, that's exact. When something's exact, there's no uncertainty. And that's great, because we'd rather not deal with uncertainty. Okay, now the next one is we need to get rid of meters. So let me continue that down here. Is there anything that you can think of that relates meters to anything else? Kilometers. 1 kilometer is equivalent to how many meters? 1,000 meters. Is that exact? Yes. And so here we don't have it memorized, the relationship between kilometers and miles, but based on these other ones, we could figure out the relationship between it.
pi here, now just multiply across, so whatever we get here, right?
Yeah. And so what I'm going to do here is this. I'm going to make sure the units cancel out. And so the inches cancel out. That leaves us with centimeters. The centimeters cancel out. That leaves us with meters. The meters cancel out. That leaves us with kilometers. So the units work out. We want kilometers as our unit. Oops. And then we just need to multiply out the numbers. Now the thing is, we are only allowed one rounding step per calculation, or one rounding. So was this 186 rounded? And it looks like it wasn't rounded. If it was rounded, then I'd start all the way from the beginning, make sure I avoid rounding. And so I would just do, I could do 186 times 5280 times 12 times 2.54 divided by 100 divided by 1,000. 299.337. Am I allowed to be this precise? You know, that's really pinpointing it. You know, to the nearest, I'm going to the nearest, like, yeah, I'm going to the nearest, okay, this is kilometers, so this would be, thousand, this would be meters. I'm going to the nearest meter here. Can I be that precise?
I think you'd be up to 2 decimal points, right? Because it was like centimeters.
Like, okay, on your next drive, let's say you're driving to San Diego, and you say, oh, my drive to San Diego, which I'm doing this weekend, is going to take me 1 hour, 57 minutes, and 36 seconds. Can you be that precise?
No.
You can't be that precise because there's a lot of uncertainty, right? There's a lot of uncertainty. I don't know how. Maybe about 2 hours, that would be better, wouldn't that? That would be a lot better than to be that ridiculously precise, because you're going to be, chances are, you're going to be way off, I think. And so the same thing in this. Are we allowed to be this precise? You know, is this like, okay, is this like trying to predict the drive to San Diego? If we are dealing with exact, then yeah, we can be this precise because these are all, there's no uncertainty here. But we do have uncertainty. Where's our uncertainty? We do have uncertainty here. 3 hours. Is that exactly 3 hours or approximately 3 hours? And approximately 3 hours, how long? How far? We don't know. This may be exact. If it's exact, then there's no uncertainty there. But if it's not exact, like it's a measurement, then there's uncertainty there.
You have 2 uncertainties, right?
Yeah, so we have potential for 2 uncertainties depending on how these are done. If this were a thought experiment and somebody said exactly 3 hours at exactly 62 miles per hour, then I can be this precise because there's no uncertainty here. Does that make sense?
What's a thought experiment again?
A thought experiment, hypothetical, it's not reality. Because in reality, are you going to get 3 seconds to the nearest, what was the smallest, femto? Pico? What was that? What was the smallest unit of time that I asked? Maybe I didn't, you know.
Atom?
You're right. The nearest attosecond. What was the attosecond significant? Normally, I don't have anybody bother with attoseconds. It used to be femto. And the only reason I did femto is because
Or the smallest unit?
it's the smallest unit that we might hear of, because in chemistry, some of these reactions happen at that time scale, the femtosecond time scale. A lot of these things happen so fast. But some things, femto is too slow, so we have atto. And so what was the significance of the attosecond?
You can see like the oxygen being broken up or something.
Yeah, right. You could see certain things happen very fast.
Also, is the most recent one.
Right, the most recent one.
The most recent measurement, synthesize is the word? Or recorded?
Yeah, well, it's not recent. It was honored recently because of the 2023 Nobel Prize in Physics was awarded for the attosecond. I mean, how do you get a pulse that fast? I mean, that's pretty brilliant, actually. So the hypothetical would be, just hypothetically, if we were exactly this and exactly that with no uncertainty, then we could be this precise. But let's say we're approximately 3 hours, you know, give or take, whatever. In approximately 3 hours, can you be that precise? No. Or let's say this were exactly 3 hours, but approximately 62 miles an hour. Should we be this precise? No. And so how do we handle that uncertainty? The way we handle that uncertainty, probably the simplest way we handle that uncertainty is by not writing this so precisely. So for example, if I'm not going to write this so precisely, I'll call it 300. You know, I'll change what we call the number of sig figs. That's the same thing as 18 karat gold. Remember we were talking about 18 karat gold? How precise is that? Is that exact? Can they get it exact to the atom? No. And so all of them are going to be approximate, and it depends on how exacting you want to be. And so we're going to talk about sig figs in this chapter too, how we're going to represent this to reflect the uncertainty over here, because uncertainty is a major topic in measurement. And so we know that certain things have no uncertainty. What things have no uncertainty? Anything that's exact. Definitions have no uncertainty. Everything else has uncertainty.
And what's for the sig figs for every, like the smoke one, you're held accountable for it? Like,
Right, exactly. So if you get 18 karat gold, do you want to get 80%? Do you want to get 80.0% or 80 point or 80.0 or 80.00? If you're a manufacturer and you're manufacturing 80%, then that's anywhere from 75 to 84%. So if you're a manufacturer and you want to save money, you always make it 75%. If you make it 75%, that's going to round to the nearest 80, right? And so you save a lot of gold that way. When you buy vinegar, you know, vinegar is approximately 5% acetic acid. You know, you could, maybe one manufacturer always makes it 4.5%. It's close enough to 5. But chances are it fluctuates. It could be anywhere from 4.5 to 5.3. So maybe sometimes you get more concentrated, sometimes you get less concentrated, because there's that randomness associated with it. But maybe some people are very precise in their manufacture and they want to make it to standard.
is that random to make some brands better than other brands?
Yeah, right. Some manufacturers are, yeah, that's true. It depends on their reputation on that, if they're honest. You know, it's like you hear about these pharmacists, unscrupulous pharmacists. They're doing, you know, I talked about chemotherapy agents. There's cases where the pharmacist is diluting the chemotherapy agent with water. So when they buy it, they're buying liquid, but it's like, you know, you've heard of the pet food and like in other things, you know, are you getting it watered down or are you getting full strength? And so this was a big issue with milk. Milk has to meet a certain minimum standard to be qualified as milk. And so it has to have a certain number of dissolved proteins and whatever else, fat and this kind of stuff and that kind of stuff. But there are a lot of unscrupulous companies watering down the milk. Well, the same thing happened in pet food. Pet food, it has to have a certain amount of protein. And so to prevent people from cheating the system and kind of watering down the protein levels, they tested it. But they didn't actually test for the protein. They actually tested for the nitrogen content in the pet food, because there's nitrogen in pet food. Well, some unscrupulous manufacturers put in some things that contain nitrogen but were inedible. And it turned out that not only were they inedible, it turned out they were poisonous. And so a lot of pets actually died from these additives that the manufacturers put in to boost the nitrogen levels artificially. Have you heard of that?
To meet standards, right?
Huh? To meet standards, right. And so this is why measurement is so important. We talked about standardization, right? And that's one of the standards that they were trying to meet with this. 14 dogs. The thing that they put in is a melamine, which contains nitrogen, but melamin's used in like plastic plates and that kind of stuff. Deaths of 14 cats and dogs that were reported.
Is melanin a compound or is it on the prerequisite only?
Melanin is a compound. It's a plastic that contains. It's cheap. You get the plastic dishes and plates at some restaurants. They're melanin. Because they're unbreakable. You drop it, it doesn't break. And so that's why they use it. But it's okay as a plate, but you don't want to eat the stuff. And so they ground it up and put it in there so that when they test for nitrogen to make sure the pet food meets the certain standard. Milk is tested too. They could put melanin in milk and boost the protein levels of milk to make the standard. And so they could water it down. But, it's these people, they're unscrupulous people. The other thing is these people needed these chemotherapy agents, and this pharmacist is diluted in half, to double their profits. Can you imagine? I can't imagine that, but I guess there are all kinds of people who cheat. But this happened. So now they're doing different tests for this. But so what we'll do is we got to start thinking in terms of uncertainty, and that's the big thing in these calculations. How precise, how accurate can we be in the answer?
So you just do 300
Maybe. It depends. We'll talk more about it. This is just the introduction to it. There's certain rules we follow. The rules are very simple. We follow these rules, and then we figure it out based on these rules here. Okay, let's look. A little girl broke her piggy bank. Inside she found 2,608 pennies. How many dollars does she have? You probably could do this one in your head. Yeah, $26.08.
So we just use division instead, just like.
Yeah, we could use this conversion factor here. This is just a one-step conversion factor.
Oh, a huge piggy bank.
Yeah, but is there any uncertainty in this answer? Here. No. Unless they miscounted the pennies. That would be the only uncertainty. It is possible they could have miscounted. For example, when they have large events, how many people were at the events? Did they scan each person's ticket, or how did they count them? So is that approximately 2,600? Those types of things. But the way this is written, you'd think, no, they counted this to the nearest penny. Versus if they said the 2,600 pennies, you aren't certain. Did they count every single penny, or they're just estimating around 2,600 pennies? All right, we talked about SI. ATO is an SI unit. And so there were some that I wanted you to memorize, but you already have a lot of these memorized anyway, so let's just talk about these ones. You probably want to memorize the big ones. I told you to memorize more than you probably really need. About the big ones would be milli, for sure, kilo, kilometer, millimeter, etc. Centi. What else? Deci, if you're in biology, but chemists don't really use deci so much, but biologists use it a lot.
Micro, right?
Micro, yes. For sure, micro. and then this one, nano, and this one, pico. Why pico? What's important about pico?
It's the smallest one up there. Before femto.
Well, it's the smallest one up here. Used to be picosecond lasers, but the significance is because of picometers. This is why we want to know pico. Picometers is really important because picometers is about how big a what is?
Yeah.
An atom. Good. Atoms are roughly how big?
What is it?
Close. 1 to 6 angstroms. I talked about angstroms, but there's the governing bodies recommending we get rid of angstroms and replace it with picometers. Atoms are about 1 to 6 angstroms, which is how many picometers? 100 to 600 picometers.
So an angstrom is 100 picometers.
Yeah, an angstrom is 100 picometers. The reason that people are saying get rid of the angstroms is because you have to use a decimal point. And so atoms aren't exactly 1. It might be like 1.23, you know. But let's get rid of the point and just call it 123 picometers instead. Does that make sense? And so angstroms are falling out of favor and picometers are replacing. And so this is atomic size in terms of diameter. So diameter of the atoms around 100 to 600. And so the biggest atoms are about 600. The smallest atoms are 100, a little less.
And for the picometer and the atom and the atomsecond, what's the atometer?
We don't, atto would be like the, size of the nucleus, let's say, or femto, Femto would be more, like a femtometer would be more like the size of what we call the nucleus of the atom, but we're not going to worry about it.
Atto is just.
Atto's for seconds, attosecond. Some chemical reactions happen so fast that you need to watch it at the attosecond. This is like, how long does it, if you blink your eyes, how long are your eyes shut for? Like less than a second? So this is like the laser. If the laser blinks its eye, how long does it blink for? Of course, it'd be best if they kept the eyelids open and watched it continuously, but they can't because you got to collect the data. And when you collect the data, you got to input the numbers, and the numbers got to be saved and this kind of stuff. So how fast can they collect the data? And so this is like how fast. It used to be you could blink your eyes for a picosecond, but it was too slow because if you blink your eyes for a picosecond, you missed it. It's already gone. And so this is why they made the attosecond laser, because the attosecond only blinks for 1 attosecond. If it blinks for 1 attosecond, then you're not going to miss it.
What he has in capturing the data, like a picture or.
Yeah, right. It's like this. It's like the old movie film reels.
Frame per second.
Yeah, it's how many frames per second. If you're a gamer, how many frames per second? Do you blink your eyes that fast? Can you even detect it? If you're running a game at 30 frames per second, could you tell the difference between 30 frames per second and 60 frames per second? Yes, you can. But how about between 60 and 120? Can you tell the difference? Are you fast enough to detect that? That would be a little harder, but of course you'd want it. You want it continuous, but you can't have it continuous. It would be too much.
Same thing with the opposite way for measurements in seconds.
Yeah, right. Same thing for the optics for the measurements, because these are lasers, they have to pulse them. And that's how that works. It used to be, because in the old days, you get a floppy disk. And the old floppy disk measured in kilobytes, hundreds of kilobytes. And then they had the high density floppy disk, which could hold 1.4 megabytes of data. I remember that because, wow, you could store a lot more data at 1.4 megabytes. But nowadays, megabytes is too small. right? And so we're looking at giga, tera, or even hertz, terahertz, your CPU.
What does first mean again?
Cycles per second. It's the laser. The laser pulsing at so many cycles per second. We'll figure it out.
Femto, the metric symbol would be F, right?
I'm sorry?
For femto, the metric symbol would be F.
F, yeah, lowercase f. Femto, you don't really. These ones are okay. These ones for sure you should know. K, C, M, micro, N, P. Those ones. Maybe megawatts.
Might be off topic, but I've heard of these Arabic numerals in chemistry before. What's that for?
Well, there's others for symbols for different things. For example, I don't know if this is Arab, like this. Have you seen this symbol before? This is, in science we call this rho, and that's usually for density. And so there are lots of symbols that are used for different things, and it's not always consistent, Lots of different ones. All right. Do you know the difference between mass and weight?
Weight is affected by gravity.
Yes. Yeah, mass is never affected by gravity. And in chemists, we don't really care because we're not traveling, to other planets or doing anything like that. And so the gravitational pull is going to be pretty much constant. Are pounds a unit of weight or a unit of mass? Pounds. Weight, yeah. Give me a unit of mass. Grams, kilograms, that would be it. So the kilograms won't change, on the moon or on Earth. But the weight will change. How do we measure it? We measure using balances. So here's some examples of weighing. Weighing things, we don't call it massing, we just call it weighing, even though we're measuring its mass.
What does SI stand for?
SI stands for International System. And so these are the International System of Units. We don't always use SI units in chemistry. In physics, they're pretty consistent. They'll use SI units. Chemists, kilograms, depends on what type of chemistry you're doing, but most chemists will use the gram. The gram is not SI. The kilogram's SI. But they're related. The meter is SI. We use that. Now, how is the kilogram defined? Do you know how the kilogram's defined? How do you know your balance is reading 1 kilogram? Well, we go out and we buy what's called a standard kilogram, and then we use that standard to calibrate it, right? But that standard, is it perfect? Is it a kilogram down to the last atom? If matter were infinitely divisible, it'd be harder and harder to get to. Okay, the old way that a kilogram is defined is this. This is exactly 1 kilogram. Do you see inside this? Inside here, there's a chunk of platinum and one other element. They use platinum because platinum is what we call Nobel metal. What's the special property of Nobel metals? They're really hard to. I talked about platinum. Remember the weird result, the weird observation with the platinum?
They're good conductors.
They're great conductors of electricity.
They don't corrode.
They don't corrode. That's it. They don't corrode. And that's one of the properties of Nobel metals. Gold is another one. Doesn't corrode. So obviously, if they made this out of iron, what do you think after 100 years? Is it going to look the same? No, it's going to rust. But even if they made it out of platinum, they're still worried it might corrode a tiny bit. And if it corrodes a tiny bit, what does that do to its mass? It screws it up. And so there's 3 jars here. Do you see the 3 jars? There's one jar here, another jar here, and another jar here. And in the jar, they don't let any oxygen in there. And so this is an oxygen-free atmosphere. And they might try to do a vacuum, but it's too hard to get a perfect vacuum on Earth. You know, lots of people have tried to get a perfect vacuum. What's a perfect vacuum? There's no matter inside. You know, vacuums can have fields inside. They're quantum fields. It could be inside Higgs field. This kind of, you could have fields, like light can pass through a vacuum, right? But there should be no matter in there. But I don't know, some recent theoretical physics stuff is pretty interesting because they're saying that there's like a quantum sponge in vacuums, and this quantum sponge can make mass and destroy mass continuously.
Doesn't that go against the law? Destroying mass, doesn't that go against the law?
Well, it's kind of interesting because they're thinking, okay, how did the Big Bang happen? You know, what was there before? Isn't that against the law? Right? But they're saying that, you know, that these things can appear and disappear based, and there was an experiment that was done. There's an experiment that was done that says the entire universe could potentially collapse into a vacuum, you know, or reappear. And so a physics experiment was done showing it's pretty interesting stuff. But that's
Maybe like random error?
no, random error is associated with anything we do. There's going to be random error. Whenever you take an experiment, there's always random error associated with it. How we deal with random error is we try to take more measurements to average out the random error. How we deal with systematic error is we try to calibrate the instrument. And so there are techniques that we use. However, no matter, you can minimize random error. This is why what I wanted you guys to do was to do a couple of things. One way to minimize random error is by having good technique, and then you can narrow it down. So the people who've done it a lot of times, they'll have less error. It's like anything, you know, if you're trying to shoot a basketball into the hoop, you know, there's going to be random error. It's going to go one way or the other way, and then hopefully it's average. But the more practice you get, the more precise you can be, and the less random error you're going to have. And so we try to do that. We try to minimize the random error, but ultimately, you can get so good, but it's impossible to eliminate. You know, there's always a chance it's going to be off. So no matter how good you are, no matter how good of a basketball player you are, can you completely eliminate random error? That is, you miss the hoop. Can you completely eliminate it? And based on quantum mechanics, you can't completely eliminate random error. You can minimize it to something very small, but it cannot be eliminated. Versus systematic error, we can completely eliminate. But let me talk briefly about this mass. This is the definition of a kilogram. This mass weighs exactly 1 kilogram. The problem with this mass is it's locked away in a vault and in France. And so if you wanted to test your balance to make sure, you can't use it because they don't allow anybody to touch this, I think, because this is the definition. So what do we do? Well, there are a whole bunch of clones made off this, but do you think the clones are exactly the same to the nearest atom? No. And the closer it is to exactly the same, the more expensive it's going to get. And so this is very expensive. And there's a lot of uncertainty because how good is your knockoff? Was it made by the person at the corner who's selling oranges and flowers in addition to the mass, or was this made in a high precision lab? You know, you don't know. You want to know this kind of stuff. So anyway, they're getting rid of this, and they want something that's accessible to the people, because this is not accessible to the people. So there's got to be a new definition. This is iridium. Iridium is another noble metal. Iridium is kind of interesting because, have you heard of iridium, this element? What's the significance of iridium? Iridium is, there's meteors, and these meteors are pretty well studied. The elemental composition of the meteors and that kind of stuff. Well, apparently there's a big meteor that struck the, I think, Yucatan Peninsula in Mexico, and contained a lot of iridium. And so when that meteor struck, it spread a cloud of iridium containing dirt and dust all over the globe. And so there's a very thin layer of iridium that marks the time of impact. And so that's where the iridium on Earth, a lot of it comes from, maybe from that layer, because it's fairly rare.
Did that change the atomic mass? Or sorry, the mass of the element? Because it was like
No, the iridium, that meteor is people, and I think it's pretty well sort of. They're saying that's responsible for the demise of the dinosaurs, that particular meteorite, or I think it's not just one, but a couple of meteorites.
Is it IR?
IR, right? Iridium, right next to platinum, PT. Osmium, iridium, and platinum are three of the most dense, and it's between osmium and iridium as the most dense element on the periodic table. Have you ever tried to pick up a lead brick? We have a lead brick. You could try to pick it up. A lead brick this big weighs about 25 pounds. So you try to pick it up with one hand. It's hard to. You have to pick it up with two hands. I'll grab it if it's still there. Last time I checked, it disappeared. But iridium and platinum and gold are a lot more dense than lead. And so if you have a gold brick, it's going to be really hard to pick up. It weighs so much. A gallon of water is 8 pounds, and that's 8 pounds is a lot. But we're talking a lot more. Okay, so there's going to be a new definition that people are looking for the kilogram. And this new definition is based on, well, you need some kinds of sophisticated instruments, but for right now, just know that that's how a kilogram is defined. Now, how is a meter defined? Do they have a meter stick in France that's locked away in a vault with 3 jars over it? Probably from 1700s or something. Do they? No. This is much more accessible. It's the length path traveled by light in a vacuum in this time frame. That's the meter. So something like this, people can calibrate there. If you have a laser, that kind of sophisticated instruments, you could do that. The SI unit for volume is cubic meter. Cubic meter is what we call derived unit. You can take a base unit, meter, and derive it a cubic meter. It's just length, width, and height. And so that's it. Chemists don't really use cubic meters. Chemists use this, cubic centimeters or milliliters. Now, there's one more definition here that you may or may not have memorized. 1 milliliter is defined as 1 cubic centimeter, so they're exactly the same thing. And so these two terms are used interchangeably, milliliters and cubic centimeters. Exactly the same. And so chemists use these, physicists will use this, the SI. So if we have the meter defined, then we can easily define the cubic meter. And so there doesn't have to be a box locked in a vault. Here, a kilogram weighs 2.2 pounds. Is that exact or approximate?
Is it the one that in the jar weighs?
Yeah. The one in the jar weighs exactly 1 kilogram. Does it weigh exactly 2.2 pounds? No. And so a kilogram weighs approximately 2.2 pounds. But what we do is we're going to do this. We're going to do it to what we call 4 sig figs. So 1 kilogram is equal to 2.202 pounds. Here. So we'll have that. All right. This is approximate, but it's fairly precise. This is approximate, but not as precise. We call this in exactly 1 kilogram. This is how we say this. In exactly 1 kilogram, there is approximately 2.202 pounds. All right, we'll take a break for 15 minutes here. So some of these I'm going to go through kind of quickly. This one you don't have to memorize, but there are different forms for this one. So what we try to do is we just try to remember one of them, and not remember all the variants of this. So for example, your book doesn't do it by pounds, how many pounds in a kilogram. Your book does it by how many grams are in a pound. And so your book will have this one, 454 grams is equivalent to 1 pound. But this is approximate too. This isn't exact. All right, just want to make sure it's recording. To be more precise, we could say it's 453.6 grams is equivalent to 1 pound. This is a bit more precise. And so it depends on which one you prefer. Do you prefer this one, the kilograms to pounds, or do you prefer grams? But we would like to know it, and we call this an indication of how precise we want to be. We call it sig figs. So this one has 1, 2, 3 sig figs. This one has 1, 2, 3, 4 sig figs. So the more sig figs we have, the more precise the measurement is. This one has how many sig figs? 2.2. 2 sig figs. This one has 4 sig figs is much more precise. So we try to use the one that's more precise. Yeah. They're all approximations. None of these are exact, like the definitions that we had. And so, in general, we try to remember things to 4 sig figs. That gives us plenty of precision for most of our calculations. Some calculations will need more, and some calculations we can use fewer. But if you're just consistent, do you want to memorize all different ones? How many is this to 4 sig? How many is it to 3? How many is it to 5? No, we just use one, and the one we use is the best compromise, 4 sig figs. We also have other units in addition to the meter. The meter is the SI unit, but we often don't use meters. We use inches, centimeters, millimeters. Here you can see the definition of an inch. 1 inch is defined as 2.54. So when we have a definition, it is exact. So this is a trick question. How many sig figs are here? 3, but that's wrong. Do you know how many sig figs we have in a definition? Infinite. Because what we see here is after the 4, do you know what we have? Zeros. And an infinite string of zeros after this, because it's right on. It's not a little bit above or a little bit below, it's right on. And so that's the zeros. And so this has infinite sig figs. How many sig figs are in 1 inch? Well, that's exact too. In exactly 1 inch, there's exactly 2.54 centimeters. However, the way we read these are a little different. And so when I go 1 kilogram, how many sig figs is that? Well, you would think that's only 1 sig fig, but it's not. It's not, because when we have an equivalency like this, we keep one of the terms exact, and then we throw all the uncertainty into the second term, or the first term, whichever one we're looking at. And so the way we read this is in exactly 1 kilogram, that means there's infinite sig figs. I can put as many zeros after this as I want, but I don't want to do that because it's too much work. And so in exactly 1 kilogram, infinite sig figs, there's approximately 2.202 pounds, 4 sig figs. So all the uncertainty just goes into one term. You don't want to say, you don't want to say in approximately 1 gallon there's approximately this. No, you want to say in exactly 1 gallon there's approximately 4 liters, if you want,
So if it's a whole number, then notice what comes after that. We can say it's infinite.
Yes. So now the definition of probably 18 karat gold is exactly 80%. No uncertainty there, but it depends on who makes it. Can they make it exactly to the atom? No, it's not going to happen. They're going to get it close, or as close, and it depends. This is why the brand might have a difference, because they might be more precise than other brands. So here we read this. In exactly 1 inch, there's exactly 2.54 centimeters. Infinite sig figs, infinite sig figs. So this is why definitions are important. We treat definitions differently because those are always exact. Infinite sig figs, whereas everything else is inexact. We have to keep track of how many sig figs and how precise we want to be. The micron, micron is a micrometer. Skip it, I think. Then we have derived units. So this is, what is this? Cubic meter? No, that's not a cubic meter. I don't know. This is a milliliter. This is by definition, although it doesn't look like it. 1 milliliter is 1/1000th of a liter, exactly. In other words, if I multiply this by 1,000, I get 1,000 milliliters, and I multiply this by 1,000, I get 1 liter. This is by definition. Both of those are exact. And this is exact too. It's exactly 1 cubic centimeter. This is a liter. 1 liter is how many milliliters? 1,000. So this is what this is trying to show. 1 liter is 1,000 milliliters, which is 1,000 cubic centimeters. So there should be 1,000 cubic centimeters there. So kilo, you should know. There are 1,000 units per kilo unit. And so this is just some generic unit. You could do meters, 1,000 meters per kilometer. You could do grams, 1,000 grams per kilogram, whatever you want. There are 100 centi units. So the only centi unit we use is meters. So 100 centimeters per meter. 1,000 milliunits. We use milli for lots of things. Millisecond, 1,000 milliseconds per second. Millimeters, 1,000 millimeters per meter, etc. And so those are the metric relationships. And you could flip it over. You could use that equivalency both ways. Sorry, let me move on here. So how many grams are in 0.711 kilograms? And so here we take our 0.711 kilograms, and then we use this relationship. Now, typically this is a measurement. And so when we have a measurement, 0.711 kilograms, there's some uncertainty there. And that uncertainty is going to be given by how many sig figs they wrote. They didn't write 0.7. They didn't write 0.71. They wrote 0.711. And writing 3 sig figs tells us a bit about the uncertainty, the plus or minus that I had talked about earlier. Because high precision means the uncertainty range is very narrow, whereas poor precision means the uncertainty range is very large. So it depends on the plus or minus range that we talked about last week or the week before. And so we know that there are 1,000 grams per kilogram, so this is just a one-step conversion. Pretty straightforward, would you say? If not, there's lots of practice problems you can do.
The conversion is definite, but the first number isn't certain. Is that correct?
The first number, the first quantity is uncertain, yeah. This is uncertain. There's 3 sig figs here. There's infinite. That means we have 3 sig figs in our final answer. And that's a good reflection of the uncertainty in it. Uh-huh.
Are there going to be questions like this in the exam, like just changing the units, or is it just to help us answer other questions?
This is that one was fairly simple. There might be like one question like that, a simple one-step conversion. Most of the conversions are going to be multi-step conversions. And so this will be a 2-step conversion here, maybe. We start off with 5.25 times 10 to the 5th milligrams, and then we convert it to kilograms. Well, here, the easiest would be to go from milligrams to grams, and then grams to kilograms. So that would be a 2-step conversion. The exam could have multiple steps. Like, how many steps did we do in converting miles to kilometers? It was like 4 or 5 steps or something like that. So the exam could have that. But the situation is, it's just 1 step at a time. Each step is no more difficult than a 1-step conversion. So if you have a complicated problem that requires, let's say, 10 steps, then each step is simple. Each step is like what we just saw. And so the exams are going to be exactly like that, but you might have to string together 10 steps. Can you do that? This is like climbing Everest. Is taking a step up all that difficult? Yeah. No, everybody can do it, right? It's just putting it all together. That's the hard part. And so each step is easy. It's just putting it together that makes the problem hard. And so so you might get stuck. You might have to take a rest. But you can continue step by step to do it. Now, some of the steps are tricky, because some of the steps aren't so easy. These are all easy steps because, these are by definition or by whatever. We'll talk about other ones that are a little bit more difficult. And so let me talk about derived units a little bit more here, since I have a little space on this slide. So let me talk about ones that might be a little bit more tricky. These are other relationships. All right, let me ask you this here. How many centimeters in a meter? There are 100 centimeters in 1 meter, and this is by definition. All right, so if I have 1 cubic centimeter, how many cubic centimeters are there? Would it also be 100? Are there 100 cubic centimeters in 1 cubic meter?
Like a million? Is it a million?
It is a million, but how did you figure it out?
Well, because you add 3 more zeros.
Yeah, pretty much. I mean, there are different ways you can figure it out. There's one easy way to figure this out. This is called a derived unit. So this is your base unit, and this would be your derived unit. And how did we get from the base to the derived? Well, we just cubed everything. And so in order to do this, what we do is we take our base unit, let's say 100 centimeters is equivalent to 1 meter, and then just cube everything, because a cubic meter is just the cube. And so what this comes out to is, it comes out to 100 cubed centimeters cubed is equal to 1 cubed meters cubed. And do you know what 100 cubed is? 100 cubed is like 10. The way I think about 100 cubed is I go 10 squared, which is 100 cubed. Do you know what 10 squared cubed is? 10 to the 6. 10 to the 6 is a million. So there's 1 million cubic centimeters in a cubic meter. So if I did a cubic meter here, I'd have 1 million of these little boxes in there. So this is derived. So this can make it more challenging, because sometimes you're given the base, or you know the base, but you have to figure out the derived. So So this is derived. Let me ask you this. 1 square meter has how many square centimeters in it? So this would be another derived. 10,000?
Yeah.
Okay. Yeah. And so we do the same thing. We know the base. 1 meter is equal to 100 centimeters. And then in order to get the derived, we square everything. And so 100 squared would be 10 squared, which is 10 to the fourth, which is 10,000. And so 1 meter, square meter, is equal to 10,000 square centimeters. So this could make it hard because, do you want to memorize these? We don't memorize these, we derive these. Some people memorize them, but I've never memorized it. I've always derived it. So these are additional conversion factors that,
We write it in the power too, because like you can say square ten or it comes out
yeah. 10 squared is 10 to the fourth, which is 10,000. Which is 10 times 10 times 10 times 10. That could make it harder than the simple. This is too simple, this problem here, but we do this on the way to other problems, so it's okay. This is another one that's quite simple. This one, though, we could go to cubic centimeters. No, that's very simple too, because cubic centimeters is the same thing. So 1,892 milliliters is the same thing as 1,892 cubic centimeters. So we don't really need to do much here. We can, because it's 1 cubic centimeter per 1 milliliter, or we just take them as the same, so they're used interchangeably here. Or we could go to cubic meters. You know, 1 milliliter is how many cubic meters? It's got to be a very small number because cubic meter is huge, but a cubic centimeter or milliliter is small. You know, it's going to be a very small number, a very large number. Okay, so those are examples of conversion. We're going to do some more of conversions in a little bit, but right now we're going to try to track the significant figures. The significant figures are going to tell us how much we pinpoint that. You know, what's the range of uncertainty in this. And so the more significant figures we have, the more precise it is. You know, does that mean it's accurate? Usually the more precision we have, the higher the accuracy we expect, but it's not always the case. You know, sometimes you could have extremely high precision, but if you're using it wrong each time, let's say I don't know how to use the precision. This is very high precision. Do you see all the markings? This meter stick is marked to the nearest millimeter. That's pretty high precision, but if I'm always reading it wrong, then even though I have this high precision, I'm not going to be very accurate.
Assuming that it's calibrated.
Yeah, we got to assume it's calibrated, but you know, this thing, does this even look straight to you? This is bent. This thing is probably out of calibration. Not only that, it looks pretty old, so it's probably shrunk a little bit too. So I'm sure this meter stick is out of calibration. I wouldn't trust it so much. You know, there's some uncertainty, even though it's very high precision, because it's marked like this. But even high precision instruments need to be calibrated. You go to the supermarket next time and look at the scale, and then you'll see the tag the last time it was calibrated. Those things have to be calibrated, I think, every year or more frequently. You know, our balances in the lab are calibrated once a year. But you might calibrate it more frequently just to make sure it's reading correctly. But significant figures is a measure of the precision. So the more precision, the less uncertainty we have. Now, the uncertainty can be thought of as kind of a range, you know. And we'll talk about sig figs. We don't want to look at this conceptually so much right now. We just want to know the rules for sig figs. So the rules for sig figs are exact numbers. Exact numbers have how many sig figs? Infinite. Now, when we take measurements, the measurements aren't going to be exact. You know? And so let's compare my meter stick with this meter stick. Is this meter stick very precise? No. And so there's a lot of uncertainty. And so the uncertainty we got to show is this is 1 meter, so I'm going to guess that this is how long?
60.
So could I guess that this is going to be point, let's say 6? I'm going to guess this is 0.6583 meters. Is that's very precise, but am I following the rules? No. Now scientists will have rules. And whenever we take a measurement, we're only allowed one uncertain digit. And so I need to know, is this, 0.6? Well, that's uncertainty. Maybe it's 0.6, maybe it's 0.7, who knows? It's somewhere around there, right? And so I'm only allowed one uncertain digit, and that being the case, I can only guesstimate this to one digit.
0.6.
Yeah, maybe 0.6 meters. They did 0.6 or 0.7. Now, the precision here is they're just taking the smallest unit. So the smallest unit is 0.1 meters. So they're just doing plus or minus 0.1. Usually we can be a little bit more precise than that, and so I took half of that because I think we could narrow it down to, so if we say 0.6 plus or minus 0.1, what that means is this can be anywhere from 0.5. Do you think that's anywhere close to 0.5?
No.
Don't you think we can be a little bit more precise than that? I think so. So that's why I cut mine in half of this, because this one is going to narrow the range. So if I cut it to half of this, that's 0.05. So that's going to be anywhere from 0.55 to 0.64. Do you think that's a reasonable range? Yeah. And so this is a little bit too broad, I think. And so most people won't do it this broad. They'll label the uncertainty a little bit narrower because they can pinpoint it a little bit better than this. But anyway, to keep it simple, they're just using the smallest unit. Now here we can be a little bit more precise, can't we? Is there any uncertainty that it's greater than 60? No, so there's no uncertainty with the 6. It's definitely 60. How much more than 60 is it? Well, here we have to take a guess. So halfway is 65, so I'd guess that this is about 63.5. Now, you're guessing the 3 and you're guessing the 5. So we're not allowed that. We're only allowed one guess, and the guess is going to be 63. So, okay, we'll guess that this is 63. We're going to guess that this is 63 plus or minus maybe a half, And so anywhere from 62.5 to 63.5, something like that. Or we might guess plus or minus 1, so anywhere from 62 to 64, Depends on the instrument itself. So let's see what they did. They did 64. So 64, they took the halfway point, and then we count. 61, 2, 3, 4. So maybe 64 or 63, depending on your guess where it lies in that range. I would have, 63 is fine, or 64. Now we can be more precise here because this is a little higher precision. Is there any uncertainty about 64? No. So it's definitely greater than 64. There's no uncertainty there. The uncertainty is how close to 65 are we? So it's 64 point what? 2. So that would be a guess. 64.2. We're getting a bit more precise here. 64.2. And the range, they're saying 64.2 plus or minus 0.1. So that would be 64.1 to 64.3 in that range. So that's okay too. Or you could do half that if you want to be more exacting. Okay, now this is a higher precision. This is like my meter stick. My meter stick measures to the nearest millimeter. Okay, so when we take a look at this, we look at it. It looks like it's,
62.
this is 64.1, 64.2. But it doesn't quite make it to the 64.2. Do you see that?
Yeah.
And so if for sure it's 64.1, there's no uncertainty there, and it's almost 2, so we'd say maybe 64.19, maybe 64.19.
Why is the end cut?
Why is the end cut? I don't know. Why? That's a good question. It shouldn't be cut. There's something strange about that. There's also something strange about this measurement here. So the measurement we ended up with is 64.19 or 0.6419. I don't know where these are coming from. So something weird with this slide. This is wrong, so let me mark that as wrong. So this is just the editor must have missed this. It should have been 0.6419 meters. So when we count sig figs, how many sig figs here? Now the rules are this 0 is what we call a placeholder, so that's not significant. Anything after the 0 and the decimal will be significant. After the first non-zero, let's say. And so this is actually 3 sig figs, we say, 3 sig figs. If we wrote this in scientific notation, we'd get rid of this 0 here. The same thing, if we rewrote this in scientific notation, it would be 2.5 times 10 to the minus 4 kilograms. You know, we moved the decimal 4 places over. So these zeros are called placeholders. And those are not significant. So this turns out to be 2 significant figures here. Those are the rules. So zeros preceding the first non-zero are not significant. Those are placeholders. The best way to learn these is to just do a lot of practice. Now, when we do calculations, we have to keep track of these. We don't want to round during the calculation. We round at the end of the calculation. So normally what I do is I carry extra digits and then round at the very end. So for example, this is 1, 2, 3, 4, 5, 6 sig figs. If I'm not allowed 6 sig figs, you know, I'll round it at the end. Let's say I'm allowed 3 sig figs. But I won't round it if this is a multi-step calculation. I won't round it continuously. So the 2 gets rounded up to a 3 because we dropped the 7. So if we drop a 5 and above, we round up. If it's 4 and below, we don't change it. We leave it as is.
What we said, how many sig figs you count?
Yeah, we follow the rules for sig figs, so we got to go to the rules for sig figs in calculations. When we do addition and subtraction, the sig figs depends on the decimal place. So here, this is the uncertain digit. We're only allowed 1 uncertain digit. And so the 5 is uncertain. And so we'll mark that as being uncertain here in yellow. Then the second measurement is more precise, and the uncertain digit is out here. This third measurement, the uncertain digit is out here, the uncertain digit's here, the uncertain digit's here. So we see if this 5 is uncertain, the 4 is certain, the 0 is certain, the 6 is certain, the 1 is certain, it's going to make this 8 uncertain. And that's going to make the rest of these uncertain as well. And so we're only allowed 1 uncertain digit, so we have to round off these excess uncertain digits, and so that we're only left with 1 uncertain digit. And so the rule for addition and subtraction is we round to the fewest number of decimal places. decimal places. And so here we have what we call one decimal place after the decimal point, and so we need to round it there. This is for addition and subtraction. And so when we do addition and subtraction, we have to line everything up like this, or we have to keep track of it in our head. But it's easier to line things up like this and then figure out. So there's no uncertainty in the 3, 8, and 9, and the first bit of uncertainty comes because of this 5 here on the 8 after the decimal.
So if the uncertainty, let's say, was at the 3 instead of the 8, we would round to the 3, or we would still
Yeah.
round to the 8?
No, we'd round wherever the uncertainty comes up. We're only allowed one uncertain digit. That's our final answer, so we'd round our final answer to one, to that. For multiplication and division, we do it by the fewest number of sig figs. So let's look at this calculation here. This is multiplication and division. So we look at how many sig figs is this. How many sig figs do you count there? Do you count these zeros here? No. And so this is 1, 2, 3. How many sig figs here? 4. And how many sig figs here? Okay, now this one is going to be 4 because these zeros after the non-zero and a decimal are significant. And so this is actually 4 sig figs. But it could be uncertain. It could have been infinite. It depends on how people express that conversion factor. It could have very well been infinite. And so we need a little bit more information to determine. But in this case, it was 4. And the little bit of more information is they measured the volume of the gas at 1.000 liters, so that's uncertain. And then they measured the weight of the gas, 1.436 grams. And so that relationship came from measurements. They got the ratio. And so this is a conversion. 1 liter is equivalent to 1.436 grams, that's intensive. 0.0573 liters, that's extensive. So we start the problem with extensive quantity here.
And then maybe round it to liters 4, or 3?
Yeah, here you take the fewest number of sig figs. So for multiplication and division, the final answer has to have the same number of sig figs as the fewest you found in any of these. So that would be 3 here. So even though we have more than 3 here, we have to round it to 3. So we're going to drop the 8. If we drop the 8, we have to round the 2 up. So it gets rounded to 3. So 0.0823 grams will be our final answer. That's sig figs. So that's multiplication and division. So what happens if we have a combination? If we have a combination, then we just look at it one step at a time. And we just follow the rules for order operations. These definitions, you need to know this definition here. We know the definition of a pound. It's 453.59237, but do you want to remember that? It's too many sig figs. So what's the best compromise? The best compromise is 4. And so I just memorize this. I drop the 9. If I drop the 9, I'm going to round this to 6. So 453.6 to 4 sig figs. But it's not exact. It's not exact, but we don't have to be so exacting because it's too many. What's this rounded to 4 sig figs? 1 gallon is how many liters?
3.785.
Okay, we're going to drop the 4, and that leaves the 5. So there are 3.785 liters in a gallon. So I said there are 4 liters in a gallon. That's not very accurate. 3.785 would be much more accurate. Liters per gallon. What's that? Yeah, right. Some people do round this to, if we round this to 1 sig fig, we drop the 7 and then round it to 4. So that's perfectly fine, but it's only good to 1 sig fig. 1 sig fig has a lot of uncertainty. So if I round this to 4, that means it's anywhere from 3.5 to 4.4 liters, which is in that range, but it's not very precise. But it's correct. There's 4 liters in a gallon. It depends on how precise we want to be. And we like to be 4 sig figs precise. 1 sig fig is not good. Do you see this triple? Triple, triple. All these are definitions. Do you know all these? Pretty much? I think most people, 12 inches, foot, 3 feet in the yard. This one most people don't know, 5,280 feet per mile. This one you don't have to memorize, but it's definition. This one, do you know this one? 16 ounces in a pound. This one I don't know. I know 1 gallon is, and then I know how many pints are in a quart. Do you know how many pints are in a quart? 2 pints in a quart. And do you know how many ounces in a pint? 16 ounces in a pint. So I know those. I don't know the quart is 32, but I know there are two pints in a quart, and each pint is 16 ounces. What's that?
We would use the screen method and went from other details, and then you'd screen it together.
Yeah, yeah.
The pint and pound are the same thing for ounces. 16 ounces.
We have to be, no, they're different. Okay, so 1 pint is defined as 16 ounces, but they're not the same ounces. We call it fluid ounces, so we put FLOZ. So there are 16 fluid ounces, liquid ounces, in 1 pint. However, there's 16 weight, this is weight, 16 ounces of weight per pound, and they aren't the same. And so a weight ounce is not the same as a fluid ounce. They're different. Unfortunately, they call them the same name. And so people get them confused all the time on tests.
What's the ratio between ounces and fluid ounces?
The what?
Between fluid ounces and ounces, the ratio.
The ratio between ounces and fluid ounces depends on what you're talking about. If you're talking about lead, you have 1 ratio. If you're talking about gold, you have another ratio. If you're talking about water, you have yet another ratio. And we call that the density. And so the density depends on how heavy it is per given volume. And so it changes. And so we can't come up with a simple ratio. It's not 1 fluid ounce per ounce. Nowhere near that. For most things. So, depends on density. Let me add that here. So feathers will have 1, and a lead weight will have another. So if you have a pint of feathers versus a pint of gold, they totally weigh different amounts. So we do metric and use SCS conversions all the time. These imperial units. And so gallons, we go from quarts to gallons, we use this. And then we can go from gallons to liters, so we use this. You see, this is the 4 sig figs, so we don't write it exact. There's too many sig figs. So if we know to 4, that's good. So we can go from gallons to liters, and then liters to milliliters. This is exact. And so here's the conversion, 1.0 quarts. How many sig figs do we have here? 2. How many sig figs do we have here? Infinite. How many sig figs do we have here? 4. Infinite. And therefore we're allowed 2 sig figs. Now I get 946 milliliters. How do I round that to 2 sig figs to more accurately represent the precision? There are 2 ways I can round this to 2 sig figs. One way is I could use scientific notation. So I drop the 6, that converts this to a 5. So it would be 9.5 times 10 squared milliliters. The second way is I can just call it 950 milliliters. 950, the zero at the end, when there's no decimal point, may or may not be significant. And so to get this to the correct number of sig figs, which our book didn't do, I do this, 9.5 times 10 squared milliliters, or 950 milliliters. This zero may or may not be significant. May or may not be significant. And therefore, we can just say 950. This is why, remember when I did 18 karat gold? I did 18 karat gold. I said 80 versus 80 with a decimal point. If I say 80, then I treat that zero as insignificant, which means this is anywhere from 75 to 84. If there's a decimal point there, then I treat that zero as significant, which means this is between 79 and 81 if you want. No, I don't know how broad you want to go, 79.5 to 80.5 or 80.4. And so having a decimal point will make sure that we know the correct number of sig figs as written. And so this wasn't properly rounded. Now we just rounded it. We use 3 different temperature scales. Here, there's Fahrenheit, Celsius, and Kelvin. Kelvin is what we call absolute. Absolute means at 0 Kelvin, there's no motion. But at 0 degrees C, is there still motion? Yeah, it's freezing. You could get colder than 0. Yeah, 0 degrees Fahrenheit, is there still motion? Yeah, these are called arbitrary zeros. This is an absolute zero. So at absolute 0, nothing's happening. But at these zeros, there is. This zero just happens to correspond to where water freezes. And that's how this is defined. The definition of 0 degrees Celsius is the freezing point of water. The definition of 0 Kelvin, we don't use degrees. 0 Kelvin is no motion, the absolute coldest you can get. No kinetic energy, right. The definition of 0 degrees Fahrenheit is what? How is 0 degrees Fahrenheit? If you want to calibrate this thermometer and make sure it's reading correctly at 0 degrees Fahrenheit, what would you do? The original way I thought it was defined, and this is just my imagination was running at this. I imagined somebody named Fahrenheit scientist, and Fahrenheit went outside and it was bitterly cold outside, and Fahrenheit said, oh, this is the coldest I've ever felt it, and I'm going to call this 0 degrees Fahrenheit after myself. Do you think that's it? That was the coldest day outside the lab that Fahrenheit ever experienced?
It's very random.
How reproducible is that? I mean, it's very random. It's not very reproducible, but maybe that's it. It's like a pound. How was a pound defined? I always thought somebody lifted up a pound and said, okay, that's 1 pound. Throw it. But if they threw the rock, then it got mixed up with all the other rocks, and you don't know how much a pound weighs anymore.
Was there actually a few named Fahrenheit?
Yes.
Last name.
Right, Lord Fahrenheit. But anyway, Fahrenheit, it wasn't. You know how it was defined? You know how to make ice cream? If you make ice cream at below 0, can you get below 0? Yeah, do you know how they make ice cream? They try to get the temperature below 0 degrees Celsius. How do you get the temperature below 0 degrees Celsius? Is it possible? If you put in an ice, it'll get to 0. Well, you could use super cold ice. Ice is not very good because of thermal. You want a liquid that's colder than 0, but is there a liquid that you can think of that's colder than 0?
The water that for Fahrenheit.
Yeah, the water that Fahrenheit used, which is salt water. If you dump a whole bunch of salt in the water, do you know the freezing point gets lower and lower? And so this was the 0 degrees Fahrenheit is the freezing point of a saturated brine solution. which is reproducible. You get a bunch of salt and you saturate it, and so and then you freeze it, and that's the temperature. And so if you have salt water, it's like if you jump in snow, it's not as cold as jumping in ice water, because the water, the heat transfer in water is much more efficient than in snow. And so that's how it was defined. Now, what we want to do is we want to come up with a relationship. And what we do in chemistry is this. So the first step is we take our observations. This will be the scientific method. We're going to derive a law here. And our observation is just some simple data. And so the data we're going to do is we're going to relate the Fahrenheit and Celsius scale. So the observation is this. When we have 0 degrees Celsius, what is the Fahrenheit temperature? 32. This is exact, by the way. And if we have 100 degrees, what is the 212? And so these are exact, which means I have how many sig figs? Infinite. So these are our observations, and normally scientists like to compile observations in tables like this. And then we look for patterns. When we look for patterns, scientists love to graph things. And so one of the common things that's done in looking for patterns, these are our observations, is to try to graph. I'm going to try to graph this. I'm going to put degrees Fahrenheit, so the temperature in degrees Fahrenheit on the y-axis, and then the temperature in degrees Celsius on the x-axis. So if I have 0 degrees Celsius, what is my Fahrenheit temperature?
32.
32. So we'll have one point here, which we'll call 32 degrees Fahrenheit, 0 degrees Celsius. Now, if I have 100 degrees Celsius, what is my Fahrenheit temperature? 212. So that gives us our second point here, 212 degrees Fahrenheit. And it turns out that this is a linear relationship. That is, it's a straight line relationship. So linear means straight line. I didn't draw it straight, but it's straight. And so the most concise definition of this pattern is using math. If we can define this pattern mathematically, then we don't have to draw a big plot like this. So how can we define it?
The slope formula?
Yeah, y is equal to mx plus b. So what is y? Y is the temperature in degrees Fahrenheit. What is the slope? So the slope is delta y. Okay, what is delta y here? Delta y is,
212 minus 32.
yeah, 212 minus 32 is what?
180.
Yeah, 180 degrees Fahrenheit divided by delta x here. Delta x is 100 minus 0, which would be 100 degrees Celsius, times the temperature in degrees Celsius. What's the intercept?
32.
Plus 32 degrees Fahrenheit. So this is the relationship, and this relationship, this pattern holds, and this is reproducible. So we call this the law. This is an empirical law. It's a law just based on observation.
What's the name of the law?
The name of the law is the equation that converts Fahrenheit and Celsius law. Nobody named this. And so, but what people do is they simplify this. And so the way they simplify this is just by rewriting this. So if I want the degrees Fahrenheit, then what I do is I take 180 over 100 is what? 9 over 5. Degrees C plus 32 degrees. And so this is the law here, the law of Fahrenheit and Celsius. If I want the degrees Celsius, I can derive it. And so this would be an equation derived from this equation, which is the degrees Celsius is equal to degrees Fahrenheit minus 32 degrees times 5/9. We don't have to get into the theory, it's not, or a hypothesis or any of that. We could just use the law, and so we use the laws.
You have to prove it?
No, we don't have to prove it. A lot of laws we don't have proof for. There's a law, have you ever heard of the laws of thermodynamics?
Yes.
There's no formal proof for it, but people have been trying to violate the laws of thermodynamics. So, for example, a perpetual motion machine that you can buy on Amazon or eBay or whatever, those perpetual motion machines violate the laws of thermodynamics. And you can see videos on machines that violate the laws of thermodynamics, but they all turn out to be hoaxes. Nobody's actually disproved it. And so the proof is that nobody's ever disproved it. That's the proof. Now, people have been trying to disprove the laws of thermodynamics for a couple of 100 years now, but not one case of a perpetual motion machine has been verified. Energy is neither created nor destroyed. So what some people do is they just plug in a light bulb with no energy source, and they're saying they're creating energy out of nothing. Have you heard of that? And which would be brilliant, because if you could create energy out of nothing, that would be free energy. Yeah. Yeah, solve a lot of problems, but unfortunately, they were all either can be explained by other means or didn't quite pan out. And people are still trying to find laws, still trying to find things that would refute the laws of thermodynamics. None have been successful. All right, we're going to come up with one more law, and that's a law between degrees Celsius and Kelvin. This one's a lot easier, so this one won't take much time. So when we have 0 degrees Celsius, it's exactly 273 Kelvin. And if we have 100 degrees Celsius, it's exactly 373 Kelvin. And so this is exact. Oops. And so we do the same thing. We look for a pattern. And so we could either write Kelvin. I'll write Kelvin on the bottom and Celsius or whatever you want. And we can come up with something. We come up with the intercept here. The intercept comes out to minus 273 degrees C. It's intercept. So degrees C is equal to the slope mx plus b. And so eventually we come up with this. Degrees C is equal to the Kelvin. The slope is 1 to 1. For every 100 we go up, we go across 100. And so it's 100 over 100. Maybe I should write that in here. So it's 100 degrees C for every 100 Kelvin. They're exactly the same size, times the Kelvin plus the intercept, minus 273. And so degrees C is equal to Kelvin minus 273, or Kelvin is equal to degrees C plus 273. So these would be the laws of Kelvin and Celsius. We only need these two. So if I want to go from Fahrenheit to Kelvin, I go Fahrenheit to Celsius, Celsius to Kelvin. That would be the easiest. So we can interconvert temperature. Now, we don't have a conversion factor to do this because the zeros are offset. And so we have two types of calculations that we do. This is the ambient temperature. The ambient is this equation here. And the other equation. And so this is calculating ambient temperature. The ambient temperature, we have to use this algebraic equation. Because the offset zeros. And so we just plug everything in here and then solve. Temperature in degrees C. Oh, this is Kelvin. We have to do this in 2 steps. So we go from Kelvin to Celsius, Celsius to Fahrenheit. And so 2 equations that we do for this. But we also have something called delta T. You know what delta, the symbol delta is used for? Change. So this is a change. This would be T final minus T initial. And we call it a change in temperature. We do it differently. So if I look at 1 degree C, a change of 1 degree C, how much did the Fahrenheit change by? It turns out the Fahrenheit changed by 1.8 degrees Fahrenheit. So each Celsius degree is equivalent to 1.8 degrees Fahrenheit. And so if I had a delta T, let's say I had a delta T equal to 1 degree C, then that's equivalent to 1.8 degrees Fahrenheit because a Fahrenheit is a little bit smaller. It's about half the size of a Celsius. Does that make sense? This is what we call a change. Versus an ambient, let's say the ambient temperature outside were 1 degree C ambient temperature. What would the Fahrenheit be? Well, if the ambient temperature were 1 degree C, then the degrees Fahrenheit is going to be 9/5 times 1 degree C plus 32 degrees. And so what it's going to be is 9/5 is 1.8, and so this is going to be 33.8 degrees Fahrenheit. So an ambient temperature of 1 degree Celsius is equivalent to 33.8. It's just slightly above freezing, because freezing is 32 degrees, right? But if I had a change of 1 degree Celsius, that means the temperature increased by 1.8 degrees Fahrenheit. So if this is 1 degree Celsius above freezing, that means we are 1.8 degrees Fahrenheit above freezing. Well, freezing is 32 degrees. We're going to be at 33.8. Does that make sense? And so there are 2 types of calculations. Delta T, we use the conversion factors. The conversion factors for delta T, I'll get to your question in a second, is 1.8 degrees Fahrenheit per degree C. And the other one is 1 degree C per 1 Kelvin. Kelvin and Celsius are the same size. And we can see this on this. Here. Let's say the temperature increased from 32 to 42 degrees Fahrenheit. How much did the temperature increase in degrees Celsius? So we had a 10 degree Fahrenheit increase here. How much would the increase be in Celsius? Maybe that's harder because it would be over 1.8. Let me do it this way. This way it will be much easier. Let's say the temperature increased 10 degrees Celsius. If the temperature increased 10 degrees Celsius, does that mean the ambient temperature is 10 degrees? No. That means the temperature increased. So I could be at 0 and increase it to 100. I could be at 100 and increase it to 110. Whatever. I had a 10 degree Celsius increase, which corresponds to what Fahrenheit increase? 18. So whatever I start off, I add 18. So that means I'm at 40. Does that make sense?
So what is ambient?
Ambient is just the temperature of the room. That's what ambient is. And so when we do calculations with temperature, we have to use two different equations. One equation for temperature changes, the other equation for ambient temperature. The ambient temperature is going to have this offset. The temperature changes won't. Temperature changes will just have the so here's some temperature conversion problems here. Let me see what else we got on proportionality and density. Well, I guess we're not really going to make it through that. Let's get some practice here. 1 second. I'll give you the some practice problems. We're going to try some more difficult conversions. All right, this will be the next. Some of these aren't that difficult. All right, you can work together. This will be your next quiz. We have 8 problems. Try to do these. We don't have enough time. Maybe we have enough time, but try to do some of these, starting off with 1 through whatever. Yeah, you can do it on the. Actually, since this is more calculations, do you have sheet of notebook paper? Do it on a sheet of notebook paper. If you don't have paper, I have some paper here. This is a quiz. You'll have the rest of the period. If you need paper, let me know.